Let's discuss effect size and post hoc analysis. These things are considered after we actually run a one-way ANOVA test. And so we're just going forward with the analysis. Let's talk about effect size first. The effect size measure that we're going to review for the one-way ANOVA is called Eta squared. And this is the symbol for Eta, right? It looks like a sort of an N and then squared, right? We're going to call it Eta squared. It's a Greek letter Eta. This measure is the proportion of variance in our dependent variable, whatever that quantitative variable that we've been studying, the proportion of variance in that variable that is explained by the grouping variable. All right. And so there's a formula for Eta squared given here. It takes the sum of squares between groups and it divides it by the total sum of squares. So that SS between is your sum of squares between groups, and that SS total is your total sum of squares. In order to determine the size of the effect, we usually use, or we can use these values as threshold values, right? And so if Eta squared is 0.1, we call that a small effect. A medium effect is about 0.06, and then a large effect is 0.14 or higher. Let's look at an example of getting the effect size. If you've not viewed the previous video on the one-way ANOVA, where we looked at an example where we had firefighters being trained under 4 different training methods, and then after we randomly assigned them to those training method groups, we gave them a test, and their test scores were the quantitative variable. This table gave us the results of that one-way ANOVA. Notice in the Eta squared formulas, it says something about sum of squares, where the sum of squares in this top row is the sum of squares between groups. And then in order to get the total sum of squares, we take this between group sum of squares, add it to the within group sum of squares, and that will give us our total sum of squares. Now, we don't have to do those calculations by hand because we can get them from JASP. And so I'm going to go back into JASP. I have the same JASP information that we talked about before in this slide. And so, sorry, on the screen here, this was our JASP. We had our data. Here's that same table. I need to adjust this ANOVA table to add our Eta squared effect size measure, right? Well, if I go to this section of our ANOVA here, under the display, I'm going to select estimates of effect size, and we can see that Eta squared is an option here. So I'm going to select Eta squared, and what you'll see is that the ANOVA table is going to add a column that gives us the estimate of Eta squared. And so that estimate is 0.503. And so remember that Eta squared came from this formula here, sum of squares between divided by sum of squares total, this value divided by the sum of these two values. So JASP, some statistical software programs give us the sum of square total, but JASP doesn't. But you can add these two totals, those two sum of squares, and it'll give you your sum of squares total. So with that, we see that that value equals the 0.503. So the interpretation of this is that about 50.3% of the variance in test scores is explained by training method, which is our grouping variable, right? Indicating a large effect size. Indicating a large effect size. Now, here we talked about the proportion or the percentage here of variance that's explained by the groups, right? So the differences in test scores, 50.3% of the differences that I see in the test scores can be attributable to the group membership or is related to the group membership of those firefighters, right? Whatever the training method was. Well, since 50.3% is explained, that means we haven't explained some of the variability. And so I want to discuss some of the variance that is not explained. The variance that is not explained by our grouping variable is explained by our within group variance. And that's given on this row that says residuals, as you recall. If I wanted to calculate that, I'm going to take the sum of squares within group, so that 3662.2, and divide that by the total sum of squares. And then we're going to see that we get 0.497 as the proportion of variance that is not explained by our grouping variable. All right. Now, you can take that sum of squares within divided by that total and get that value, or you can just subtract your eta squared from your between groups, from your explained variance. You can subtract that from 1, and that'll give you the same value. All right? But this eta squared is important because it can tell us how much of the variability that we see in our data is attributable to our grouping variable, and it can tell us when we looked at the unexplained variable how much of that variance is explainable by other things. It can be measurement error. It could be some variable that we didn't include in our study. It can be anything else, but we hadn't explained it because the only thing that we contributed to the study was the different groups, right, by our research design. And so we can explain some variance and tell how much we're explaining, and we can get the amount that we're unexplaining or not explaining by looking at our eta squared. And that's our effect size measure. The last thing I want to talk about when it comes to one-way ANOVA is what we call post hoc analysis. Post hoc, right? After we've done that global F test, all right? So after we've done that global F test and we find significant results, excuse me, then we're going to run post hoc analysis so that we can determine which of the groups are actually significantly different, right? Yield significantly different means. And there are several different methods upon which we can do that. But generally, what we do once that post hoc analysis, our significant one-way ANOVA has been found to be significant, we can conduct a bunch of pairwise t-tests now that we know that the results are significant. And when we do this, what we do most often is a method called Bonferroni correction. So there's a statistician. The method is Bonferroni correction method. This method involves doing a multiple comparison where you adjust your significant level so that you can reduce your type 1 error. And so what we're going to do is we're going to use an alpha adjusted by taking our original alpha and dividing it by the number of comparisons that we're going to make. All right. If I do that post hoc, I'm going to maintain my type 1 error rate, and I don't have to worry about that inflation that we saw in the type 1 error rate if we were to try to start with a bunch of multiple comparisons using independent samples t-tests. All right. So let's look at an example where we do this. It says for the firefighter training method and test score example, conduct a post hoc analysis in JASP to determine if groups A and D differ significantly. Well, when we're doing these post hoc analyses, this is going to look almost identical to the independent samples t-test, or if you want to say 2 sample t-test, that's fine, right? If I want to know if these 2 groups will end up with significantly different means, then I'm going to use this as my null and my alternative hypothesis. Mu sub A equals mu sub D as my null, and my alternative is mu sub A is not equal to mu sub D. All right. And then I can go to JASP and I'll show you how we can run that. So I still have my information here from my original analysis. What I'm going to do is I'm going to scroll till we see post hoc tests. I'm going to put my factor, my grouping variable, in this box here. And these are some different methods to correct for the type 1 error rate. The default is Tukey. That's another method that some statisticians use. I'm going to do Bonferroni here. As you can see, it's loading another table. And I'm going to the table that says post hoc tests. And this is my results for doing post hoc comparisons. Now, I want you to make a note here. It says the p-value has been adjusted for comparing a family of 6 estimates, right? So that means what JASP has done is it adjusted the p-value. So when we do these comparisons here, we can still think about it in terms of 0.05. So I know in that previous slide, I said that the Bonferroni adjusts your alpha by doing alpha divided by the number of comparisons. Well, so that you won't get confused and think you have to do all of that, JASP has given you a p-value with the Bonferroni adjustment already. And so we can compare these p-values to our original alpha, which is 0.05. So don't worry about doing the divisions of alpha to see if something is significant. Still use your regular 0.05. Notice also, instead of this saying P for p-value, it says P with a subscript bond for Bonferroni adjustment or correction. So remember, what we're doing here is a bunch of t-tests, independent samples t-tests. That is why we have a test statistic and some degrees of freedom here. But what I'm going to do is go back to our notes and show the results there. And so our goal was to compare A and D. So this first column has A, and this row here has D. So all of the information for the t-test comparing A and D is here. So I know I have a Bonferroni corrected p-value of 0.035. That p-value has been adjusted, so I still can compare it to 0.05. And so since that is less than 0.05, I reject the null hypothesis, and I say that there is sufficient evidence to conclude that the population mean test score for firefighters in training A is significantly different than that for training group D. All right. And so I can do multiple comparisons, right? So I know that A and D have significantly different mean test scores in the population. The same thing holds for A and C, B and C, and those are the only ones that are significant. So A and C, A and D, and B and C. A and B have a very large p-value. B and D has a large one, and the one for C and D is greater than 0.05. All right, so we only found those others to be significant. All right, the next slide has an example of some write-ups for APA style type write-ups. I'll let you read that on your own. But I do want to look at this last example with post hoc analyses. We hadn't talked about confidence intervals here, and there's a special graph that we can use that can also help us compare groups, right? So for instance, if we wanted to know if one group performed the best out of all compared to all of the other groups, or another group who performed the worst compared to all of the other groups, then we can create a graph that includes error bars that represent like 95% confidence intervals for those specific group means. And then if those error bars or those confidence intervals don't overlap, then that's evidence that the groups perform significantly different from one another, right? So in the same box as the post hoc analysis, I'm going to go to display, and I'm going to, actually, I don't think it's this one. It's not in the post hoc, sorry. It's in the descriptive plots here. I'm going to put my grouping variable in the horizontal axis, and I'm going to create a descriptive plot that plots the actual means of these groups but I want the confidence intervals for those group means. So, for instance, this first group A had a mean of 63.2. Remember, confidence intervals are centered at the sample estimate, and then you add and subtract your margin of error, and then you get the actual values of your confidence intervals. That is given by displaying error bars here, and I'm going to stick to 95% confidence intervals, right? So my 95% confidence interval for this one starts at about, I'm estimating here, a little over 65, maybe 66, and goes up to a little before 70, right? And so this is a graph that I can use. I'm going to go back to my notes because there were a couple of questions that we want to answer. Did one group perform best and one group perform worst? Well, if I want to know if one group performed best, I'm going to look for the group with the highest mean, which is this one here. And I want to look at whether the confidence interval, which is denoted by those error bars, overlap with another group's confidence interval, or if it's non-overlapping with any of the groups. And so since group C had the largest mean, it's the candidate for the group that performed the best. However, since the confidence interval for group C overlaps with the confidence interval for group D, that means in the population, the mean for C and D could possibly be the same value because their confidence intervals overlap, right? And so, since C overlaps with D, I know that there is no group that performed the best. Now, the answer would be C if that confidence interval did not overlap with D, so it would have been much higher. Did one group perform worst? Well, in order for me to do that, I go to the group with the smallest mean, which is group A, and look to see if its confidence interval overlaps with the confidence interval of any other group. And of course, we see that A overlaps with B and C's confidence interval. And so there is no group that performed the worst here. All right. And so the answer to those two questions would be no. Again, look for non-overlapping, and the largest non-overlapping would be the best performance. The smallest non-overlapping confidence interval would be the worst. That concludes our introduction to our one-way ANOVA, one factor. Look at some of the other examples in your practice problems. And once you get this one-way ANOVA nailed down, when we extend this to two factors, it'll be a lot easier to understand. We'll see you in the next video where we'll talk about the two-way ANOVA.